Hello and welcome to my talk at Embedded Online Conference. Today we are going to talk about simulation. We will probably cover my personal story and why I started working on Wokwi. We will see some of the simulations in action, how to build your own virtual hardware into the simulation, how to simulate in your favorite development environment, Visual Studio Code or JetBrains IDEs, and a little bit about how it works and how you can harness the power of simulation in your CI environment. So let's get started. Who am I? My name is Uri Shaked and I am a maker. Software, hardware, PCBs, electronics, 3D printing, custom ASICs, you name it, I like it. And today I'm working on two projects, Wokwi.com, which I'm going to tell you all about in just a few minutes. And the second one is my other hat, is the ASIC hat. I'm working on tinytypo.com at making custom chips, custom ASICs more affordable and accessible to everyone, together with Matt Venn, who is also going to talk in this conference. Why I started Wokwi? Coming from web background, I was used to have blog posts with code snippets that you could actually run and experiment with. And when I started blogging about my hardware projects and Arduino, I wanted to bring the same experience to my blog post. And later, I even started working on my own Arduino course, and I wanted to have those interactive code blocks that users could just run and try in their browser. So I started working on a JavaScript-based AVR simulation engine. But the turning point was when I started working on my first hardware crowdfunding campaign. Let me introduce to you the skull. This spooky skull is an actual hardware CTF, capture the flag riddle, a pretty complex one that you are invited to try to solve after the talk. If we take a look at the schematic, we don't actually need a schematic. There is a small 80Tiny45 processor. This grill, when you touch the grill, it actually blinks its eyes in a spooky way. Two LEDs for the eyes, current limiting resistors, battery, of course, you need one, decoupling cap, and this is just a pull-up for this grill. So simple hardware, but challenging riddle. And now, please forgive me, but I'm going to give a little spoiler on how to approach this riddle. So if you don't want a spoiler, stop watching. The way you are going to control the skull is by shining light on its eyes and then using the photovoltaic effect that would create voltage on the LEDs, and that would be detected by the ADC in the 80Tiny. And for me, while working on the firmware for this riddle, it meant that I had to test it on many different environments and with many different light sources. Overall, I had like 40 different scenarios that I needed to test. Each scenario would take around 3 minutes, and they would need to be in different times of the day, daylight versus night. So with just 3 days that I had to finish the firmware, that was very challenging. Luckily, I had Wokwi, that simulation engine that I created for the Arduino course. So what I did was spending about half a day recording a bunch of different scenarios in different lighting conditions and with different illuminating devices, and captured all the analog readings from the 80Tiny ADC. And then I hacked together some environment where I could run all of those scenarios in parallel using the Wokwi simulation engine. And you know what? Let me just show you how it worked and how I used that to iterate on the firmware. On the left side of the screen, you can see the source code for the skull's firmware. So this is what I had to iterate on and get to a perfect state in just 3 days. And on the right side, this is the web page that I hacked together, and let's just add a comment and save. And you will see now it's just going to run all the test benches, test all the scenarios that I had in just like 5 seconds. And then I can see that 27 tests were passing. And now we are going to change the code a bit. This is just the process that I went through when I worked on this project. So let's actually implement this low pass filter. So filter minus equals, let's shift it by 4 bits, for instance. and add a value. Thank you, Copilot, and return the filtered value. And now it's running the test suite again, and we can see that we went up from 27 to 40 passing test cases. And if we just, I don't know, try to tinker with the value, and the tests are now running again, and we can see that just by changing this value, we got down to 38. So this value is actually worse than the previous value. So to summarize my Skull firmware experience, it took me about half a day to record all the data for those different test scenarios, and then about another day to set up this automated test running system that you have just seen. But then I was able to cut down my iteration times from a few hours per iteration to just a few seconds. And I was actually able to complete the Skull firmware within less than 2 hours. And for me, that was a transformational moment. I realized how much value Wokwi and simulation in general could bring to embedded developers, and how much time and effort it could save when iterating on your firmware. And that's why Wokwi. If you want to learn more about the Skull or what I learned from running a hardware crowdfunding campaign, you can find links in the slides. But now let's move on to the main star of the show, the simulator. We will start with a light and fun example. They say, just because you can doesn't mean you should. That's true, well, unless you have unlimited virtual hardware. On the left side of the screen, we can see the source code for this example that one of the Wokwi users wrote. And on the right side, we have an Arduino Mega surrounded by 32 different servos, and if we start a simulation, we can see them starting to move randomly and then slowly starting to dance. Dancing servos for sure are a lot of fun, but it wouldn't be a great hardware talk without the obligatory blink. And in order to make the blinking lights a bit more interesting, it's not just the standard Arduino blink, it's actually STM32 HAL powered blink. And for extra nerdy points, we can even bring up GDB, set some breakpoints, and the firmware would pause whenever we hit the interrupt handler and toggle the LED. And since this is virtual hardware, there is no limit to the number of breakpoints that you can have. This is a fully featured version of GDB running right inside your browser, and it's only one way to debug your simulated firmware. We will see another way to debug later, but for now I want to move on to another example and talk about the labels that appear next to the MCU pins. In this project we have an ESP32C3 connected to an LCD TFT display, and whenever we start the simulation it does nothing. We expect it to print some text, but we can see that some of the connections are missing, namely the SPI clock, which is quite important. And if we pause the simulation, we can actually see the actual functions of each of those pins. We could try to find which pin is the clock in the source code, but apparently it doesn't even appear in this source code because it's defined somewhere deep in the Arduino libraries that we use here. So in this case, we can see that pin 4 is the one that we need to connect to the clock. Let's pause the simulation and make this connection. Start the simulation again. And voila, it's working! I call this function pin dump. Just pause the simulation and then you will be able to see the current state and function of each pin in your board. And now on to the next example. We have an ESP32 LED and a button and some ESP-ADF code that listens to button press interrupts and sets button press to true. And whenever you press the button, it just toggles the LEDs and prints a star. Let's start this and see if it actually works. We click on the button and oh, the LED didn't toggle and there are 2 stars, and now it happened again. What's going on? To find out, we'll stop the simulation, zoom out a bit, and then add a logic analyzer part, connect the logic analyzer to the button, to the LED, And for extra fun, we'll also get it connected with the TX port of the ESP32. And now we are going to run the simulation again and click on the button twice. So click once, click twice, and let's see what we recorded. It downloads a VCD file to my computer. I open it in Pulse View, and now if I zoom in on the button signal where it was pressed, I can see that the simulated button was actually bouncing, and that's probably what caused the problem. And if I wanted to debug even further, I could add this UART decoder and specify which pin was the TX line. And then Pulse View would just show me the messages that were sent through UART. If I set the data format to ASCII, I can actually see the star in the new line that my code printed. So you can use the virtual logic analyzer to record your signals, and then you can see what's going on in the wires and even decode complex protocols. If you love Python or the PyPico, then this one is for you. It's a seemingly simple MicroPython program that animates a NeoPixel display, but behind the scenes it actually contains a lot of complexity using the RP2040 PIO peripheral. And this is a great opportunity to take a look at the PIO debugger. We are not actually going to debug this, but basically you can just step over the PIO instructions and see the register values, how they change as you step through these PIO instructions. And remember, if you ever need to work on the Pico's PIO, Wokwi is your best friend. And now for something completely different, IoT. Here we have an ESP32 DHT temperature sensor and some MicroPython code that connects to an MQTT broker and then reads from the sensor and reports the weather to this MQTT broker. To see it in action, we are going to open a web-based MQTT client that will connect to the same MQTT broker, and we are going to subscribe to the Wokwi weather topic, which is where the MicroPython code is going to send the MQTT messages. So let's subscribe. Put the windows side by side so we can see both. Start a simulation. The ESP32 is now connecting to the virtual Wi-Fi and to the MQTT server, and voila, we can see the message. And if we click on the DHT22, change the temperature, we can immediately see the message in the MQTT broker. And now we are going to download the pickup file where we can actually see the network traffic. So filtering for IP traffic, we can see the DHCP messages. And if we scroll a bit down, we can see the actual MQTT message that our simulated code sent to the MQTT broker. So Wokwi has virtual Wi-Fi, but with real internet, and you can even see the network packets. Isn't that cool? And now, finally, we will see one of the paid features of Wokwi. Until now, everything was just free. This code is an HTTP server that runs on the ESP32, and we are going to connect our browser on my computer to this HTTP server running inside a simulation. For this to work, we need a special program called the Wokwi IoT Gateway. It's running on my computer, and when I'm running the simulation, it will connect to this IoT gateway. And now the HTTP server is running on the ESP32. I can switch to a split screen layout, connect to localhost 9080, and my web browser is talking to the HTTP server inside the ESP32, controlling these two LEDs. So, using our open source private IoT gateway, you can connect from the simulator to your local network and even the internet, or you can also connect from your computer or browser into the code running inside the simulation. Now, Wokwi has many parts and sensors built in, but we definitely don't have everything. What if the part that you need doesn't exist yet? Well, don't worry, there is a good chance that you can create it yourself using the Wokwi Custom Chips API. The Custom Chips API allows you to create new simulation models for displays, sensors, memories, and even test instruments. You can write a code in C or any other language that compiles to WebAssembly, such as Rust. Let's see some examples. In this case, the user wanted to create a project using the LM75 I2C temperature sensor, so he created a custom chip for it. custom chips use a JSON file to define the pinout, and for sensors also their inputs. And then there is a C file where you can define the chip's logic, such as in this case the behavior of the I2C and how it responds to I2C connections and read events. When you start a simulation, you can actually see how this new sensor interacts with the system. So we can set the AC temperature, or if we change the values of the sensor, we can see the value, wow, that's pretty hot, changing on the screen. For the next example, we have a popular YouTuber who wanted to use the SH1107 display for the project. So we created it using the Custom Chips API. Just like the previous example, we defined the pinout inside this JSON file and also the dimensions of the display. And then we go ahead and write all the logic like the command decoding and the I2C logic, frame buffer handling, and that kind of stuff inside the C file. And when we are done, we can just click play and enjoy the display simulation model we have just created. My favorite one comes from David Lloyd, who used the Chips Display API to create a real-time scope. In this example, we have an ESP32, a stepper motor, and of course, the scope chip that is connected to the signals of the stepper. And if we start a simulation, we can observe the signals, and you can see how the signal timing changes whenever the motor changes direction. It also shows the signal frequency and the duty cycle. And if we zoom out a bit and click on the scope, we can change the settings such as the sample time, and now we can see the active and idle time of the stepper. This scope is not something that we built into Wokwi. I just love the creativeness of our users. And unlike the previous examples, the code for this custom chip is loaded directly from a GitHub repo, so it's easy to copy the part, stop the simulation, copy the part, and just paste it into your own project. And if you are interested, you can find the code on the GitHub repo of David Lloyd and read the documentation, see the examples, and get inspired to create your own custom chips. And here is something that we are currently prototyping for Tiny Tapeout, custom chips written in Verilog. This one is a Simon Says game, LEDs, button, score display, a speaker, and the star of the show in the middle running with a 50 kHz clock. Let's play! Oops, I failed! By the way, I just sent this design to be made into a real chip on Tiny Tapeout 6. The long wait. To learn more about the Custom Chips API, check out the documentation. It has full reference of the different APIs, a bunch of useful chip examples, as well as some YouTube tutorials from Psychogenic Pat.
Hey, I'm going to show you how to implement a custom chip to include in digital simulations using Wokwi from A to Z.
Up to this moment, all the examples that we have seen run inside the web browser. This makes them super easy to share. Just send someone a link and they can open and run the project on their computer. But when working on a real-life, complex embedded systems project, you usually want your fully featured IDE like Visual Studio Code or JetBrains. Well, you can. This is an ESP-IDF project that displays some text on an I2C LCD. Let's start a simulation and see it in action, and put a simulator side by side, and you can see it says welcome to Wokwi, and then if we press any key on the terminal, the code moves on and prints more stuff to the screen. Now let's say we want to change the greeting. Hello, EOC 2024. All we need to do is just click on build, wait for a few seconds, and voila, we can see the result. No need to wait for flashing. Actually, our partners at Espressif have coined a term for this, Wokwi style of development. Now let's set a breakpoint just before printing the greeting and restart the simulator in debug mode. Then press F5 to start the debugger. and run the code up to the breakpoint. And we can see the I2C screen was initialized, the backlight is on, and if we step over, the greeting will be printed. And as you would expect from a debugger, we can look into the variables, see their values. And now let's make some chaos inspired by Alicia White. Set some pointer, this SMBus info to null, and check how the program deals with it. Continue. Terminal. Oh well, they actually anticipated this. Good job, whoever wrote this code. The cool thing about using Wokwi in VS Code or JetBrains is that you can use any language like Rust or Zig and embedded OS like Zephyr Project, FreeRTOS, Nuttix, and as long as you have a firmware binary, Wokwi can simulate it. This example comes from Benjamin Kabe from the Zephyr Project team. We can see that each directory has a wokwi.toml file that defines the firmware to load and a diagram.json file that defines the schematic for the simulation. Let's start the simulation, hide the sidebar, and explore the Zephyr project shell. I'm trying to read from this sensor an MPU 6050 connected to this ESP33S3. And now let's set a new temperature and read the values again. It worked! Now for the fun part. This one is for Alicia White, another attempt at creating chaos. We'll write some evil value to the stack and boom! Mission accomplished. So, after having lots of fun smashing the stack, let's talk for a minute about how Wokwi works. We execute our code one instruction at a time, like a real microcontroller would, and we also simulate the common peripherals like I2C, UART, SPI, the timers, DMA, etc., and the registers. The simulation engine is written in JavaScript, and it supports ARM, RISC-V, Extensa, and AVR. Some of the simulator code, like the Raspberry Pi Pico, is open on GitHub, so you can take a look and learn. Or if you have a lot of patience, you can also watch my recorded live stream, where I coded the Pico simulation from scratch. Originally, I planned to show how to use Wokwi from the CLI, write test scenarios to automate testing, and run the simulation on GitHub Actions so you could use it for continuous integration. But then I realized that Tim Gate already did it in his EOC talk Embedded System in X Flavors. So just go and watch it instead. Well, that was quite a journey. I spent over 20 hours planning, recording and editing this talk, so I really hope that you enjoyed it and found it valuable. And if you want to chat, you can find me on the Wokwi Discord server at wokwi.com/discord. I would love to hear about your experience using Wokwi and how you used it in production and all that kind of stuff. Well, thank you. I hope you have a great time at the rest of the conference, and bye-bye.